Okay, welcome everyone to this XENON webinar, the first of our Tech Talks for 2020. I'm really pleased to have Werner Schultz here and Peter Kearney from Intel. And today we're going to talk about Intel Optane memory, dive into a little bit of the comparison between Optane and DRAM and where Optane can really benefit your HPC workloads, and look at some examples and talk about a POC environment that we're setting up and we'll have available. Peter's also going to take us through some of the Intel roadmap. And yeah, welcome to the webinar. A bit of housekeeping. If you have any questions, please pop them into the chat. We are going to go through the webinar content, probably about half an hour, so there's a bit of discussion at the end. And we do have a semi-large group, so welcome to everyone for coming along. If you pop your questions into chat, we'll hit those at the end. And with that, I will turn over to Werner to start the slide deck and get us going.
All right, also from me, welcome everyone to the webinar. And I'm going to share the slides here, which you'll hopefully see on your screen. So welcome everyone. So today we're going to talk about Intel Optane persistent memory technology and show you a few examples in high performance computing. And we'll kick it off here with the agenda. So John, you want to talk us through the agenda and the first introduction of XENON systems, and we'll go from there.
Yeah, that'd be great. That is our agenda. Let's go on to the next slide. I think we've covered that off. We know what's coming up. Just a bit of a background for those of you who are not familiar with XENON. We were founded in 1996. We service customers right around the country, and we do sell systems internationally as well. We're renowned for our HPC expertise and building specialist server systems. And we've branched from there into AI and a whole bunch of other related fields. I think the use cases for HPC and AI are really exciting now, and they stretch from the smaller clusters that are used in manufacturing and design right through to the really big research clusters like at NCI. So that's us in a nutshell. The timeline, as you can see we've had a long history in HPC, from delivering some of the first GPU systems in 2007, 2008 for CSIRO and VPAC, through to the more recent work at NCI. I'd also point you guys to our new website where there's this timeline is updated and the case studies refreshed. There's a lot of really interesting new content there, and we are adding new content weekly, things we're doing with some of our new solutions and the things like this around Optane. So we look to really bring you the latest great new things from the world of HPC and AI. Thank you, Werner.
Thanks, John. And maybe just to add to the timeline here, while we have this nice overview of XENON systems here, we have really a long history in high performance computing, not only in the classical sense of HPC centers like NCI or CSIRO or others, but we've also been working with industry and large corporations on other workloads like render farms, for example. And that was really one of our first projects. And if you've watched the Matrix movies, most of the special effects in the 3 Matrix movies that have come out so far were rendered on our equipment on CPU clusters. And I think I just recently read that there is a Matrix, a 4th version of the Matrix movies coming out soon, for better or worse. The other interesting aspect is that we're also covering a lot of different verticals. We're working not only with universities and research and education facilities, but we're working a lot with industry and also with government, where we see the need for high performance systems in general increase a lot. And that covers now not only the compute aspects of servers, but it also covers storage systems and the networks and fabrics which tie it all together. And it's really that intersection of compute and storage which start to depend on each other even more than they have in the past, where it gets really interesting. And so with that, let's talk about Intel Optane persistent memory technology a little bit more, because it's really interesting where that fits in the technology stack. So when you look at the technology stack, and especially on the memory stack, of course, on the bottom, we have the large capacity systems based on still hard drives and tape technology. In order to get more performance, the introduction of flash memory has really enabled a lot of new workloads and configuration architectures. And Intel is, of course, providing a lot of devices and solutions there with its 3D NAND technology. The NAND chips, of course, get combined into NAND SSDs, which are then used for large flash arrays. And on top of that, Optane can also be purchased in the form of solid-state drives, which behave essentially just like a conventional SSD, but they give you a lot lower latency and a lot more performance. And what we're really focusing on today is that gap now between the storage devices like the SSDs and the memory on top of that, which is the main memory in your servers, the DRAM chips, then the in-package memory that's nowadays embedded in the packages of the CPUs themselves. And of course, then you have at the very top of the storage memory pyramid here, the caches, which are tightly embedded into the CPU designs. And where we really have this gap is between the SSDs and the DRAM, where we see a lot of demand for large memory systems for applications which require a lot of memory, but investing in DRAM is very often prohibitively expensive. And so researchers, engineers, data scientists try to make all kinds of trade-offs to just live within the budgets they have to purchase systems and equip them with DRAM, while facing the reality that they can never get as much DRAM as they would want to. On the other hand, using SSDs, and in the simplest case, as a medium to store intermediate data is also just a problem and a poor gap filler. And so what we really need to do to fill this gap here is to look at Optane persistent memory technology. And the idea really is that we can use the Intel 3D crosspoint technology in the form of Optane memory modules in the end in the servers, and now we can use them in actually various different ways, which we'll get to in a few slides. And this way, Intel Optane is really able to fill that gap between conventional flash SSDs as well as the Optane SSDs on below in this pyramid and the DRAM on top of that. And now suddenly we have a tier there that allows us to get us almost DRAM-like performance with extremely low latency, but much higher capacity, even in 2-socket servers, which are very affordable, and we can get it at a price point that's much closer to SSDs than to DRAM. And it's not only then the Optane modules in the form of the SSDs or the memory modules, which are being which can be integrated into servers, of course, but we see also a lot of interesting storage technologies now taking advantage of the Intel Optane technology. And that includes the Intel Deos project, which is really aiming at providing exascale storage systems for high-performance computing centers at this time. So we're not even talking about terabyte SSDs or petabyte storage systems. Intel is working there on exabyte-sized storage systems for the next generation supercomputers. And we're also working with partners like VAST, who are integrating the Intel Optane technology into their storage systems as an extremely fast, low latency storage tier that's transparently integrated into their system, and which is really designed to pretty much cut off the pyramid on the bottom and become a universal storage architecture that does not require hard drives or tape anymore, that can be all solid state memory with flash and Intel Optane technology. So Intel Optane DC persistent memory really introduced an entirely new tier of storage solutions with performance levels that have not been accessible before. When we look at it in a storage mode, it gives us really very low latency. Therefore, it supports then much larger data set, and it can deliver those data sets to the compute appliances much faster. And Optane also has the advantage that it has much higher endurance than conventional flash SSDs, which suffer from wear out problems, especially in the triple level cells and in the new quad level cell designs. And that's really where Optane shines, that it does not have the endurance problems. And on top of that, it has much greater bandwidth, which overall leads to much better storage performance. Of course, it can also be essentially used as a caching layer, where it again supports much faster processing. It allows much higher utilization of the systems, and we'll have a few more examples there for real-world workloads in a second. And just another motivation, why is Optane technology nowadays so relevant and becoming so useful? When you look at the graph on the left, where you can see the different DRAM densities, meaning the chip sizes going from the 1980s with 1 megabit wall chips to 4, 16, 64, all the way to today's 16 gigabit DRAM chips. You can see already how this slope in this graph is changing, where we can identify first phase in the 1980s and early 90s, where we saw a density increase, meaning a capacity per area in the chips of about 4x every 3 years. That then was followed on by a second phase, where it was growing only by 2x every 2 years. And today, we're really in this third phase, where because of various process technology challenges, it has really slowed down to about 2x density increase per 4 years. And the challenge with the density increase slowing down is really that because the price of DRAM in particular and semiconductor chips in general is very closely tied to the area of the chips, which in the end means because of process challenges, especially with the lithography processes which are involved in the manufacturing of the chips, if we cannot pack more bits onto the same area, that means in order to buy more capacity, we have to buy more chip area and we have to buy more chips, which in the end makes it more expensive. And so that's why this slowdown is becoming a problem. And that's illustrated on this graph on the right, where you can see on a normalized scale how the capacity has been scaling. And here in the first line for the phase one, the white line on top, you can see that 4x increase every 3 years. The phase two and phase three, of course, are here much lower. And the real challenge is that when we look at the growth of data in general in use and being produced by computing systems worldwide, we need more than a 2x improvement every 3 or 4 years. And so now in phase three, where we're at now in these years, the problem is that the chips are not scaling as fast as the data is growing in the economy. And that's really becoming now a financial problem, because we essentially have a hard time keeping up with building storage systems at economical price points which satisfy the demand for data. And that's where we need a new tier there that provides us with capacity and that provides us with the performance we need, and that can keep up with the growth in data worldwide today. And as we've seen in the pyramid before, that's where Intel Optane persistent memory technology can provide a lot of value, because it can provide the performance, it can provide the low latency at a much better cost point than DRAM, and with a much higher endurance and performance than conventional SSDs. And we can see that when we look at hybrid cloud applications, infrastructure as a service or virtualization architectures, where we can increase the density in virtual machines at the same cost. And we can typically, what we've seen and what Intel has observed and reported is that they can get about 1.2x more VMs onto the systems while meeting the same SLAs. So that means the providers can offer now more capacity on their systems. They can put more VMs on their systems and recover their cost a lot faster. When we look at database services and data services in general, the important aspect is to reduce the cost for a given capacity. And there, for the really large systems with 8 sockets, we can get now 36 terabytes of Intel Optane persistent memory into a single server. And that is, again, enables either packing a lot more VMs onto the same systems, or we then can host much larger databases in what's effectively memory, but at a much lower cost than memory, enabling to run those databases, and especially then to run the processing afterwards when we do analytics on those databases much more efficiently and much faster. And for fast storage solutions, the increased storage really then comes only at a slightly higher cost. So we can increase the capacity a lot faster than the cost per system goes up. And the data performance there per system dollar spent is now higher than 1. So you get you get more performance out of the system for essentially the same dollar spent. So that really means for in-memory databases, we can provide now much higher capacity, we can run larger databases, reliability goes up, and recovery becomes a lot faster, and we essentially get the performance of memory without having to pay the cost of memory. For virtual machine hosts, that really means that we can now increase the memory per virtual machine using Intel Optane persistent memory modules without having to pay the price of DRAM. That increases the efficiency of the infrastructure while keeping cost at bay, and therefore makes the adoption a lot easier. And so these are really drivers which now enable much higher densities, reducing cost and increasing performance with Intel Optane technology. And here are a few examples based on real-world workloads. When we look at the databases, for example, in conventional enterprises, of course, which run a lot of ERP systems based on SAP, performance improvements on the order of 2.4x have been observed versus the existing servers installed in various enterprises today. For virtualized database instances with Microsoft SQL Server, for example, 36% more VMs can be run while keeping the cost essentially similar to the existing infrastructure. Similarly, for analytics workloads with Apache Spark, for example, their architectures with Intel Optane persistent memory have shown to produce about 8x faster queries compared to conventional systems with DRAM and hard drives. And FileSide, for example, reported 37% more transactions per second than conventional systems. And in the virtualized infrastructure and storage world with VMware vSAN, for example, we can host 60% more VMs per node. So the cost per VM goes down dramatically. And for hyperconverged infrastructure, also, about 36% more VMs can be hosted with Microsoft Azure Stack, for example, on-prem at a similar cost. So these are quite typical workloads in corporates and enterprises, and we'll have a look at the HPC workloads then later on in the slide deck here. And so with that, I'll hand over to Peter Kearney. He will take you through some more of the details here of the operating modes and the roadmap for Intel Optane.
Yep, thanks, Werner. So I'm Peter Kearney. I'm a technical specialist solution architect for Intel based in Sydney. So I'm going to talk to you about, all right, well, how do you make use of this stuff? How do you configure it and build it? And how does it work? So in this first slide, to look at the operating modes, the product can operate in two different modes. It can operate in what we call app direct mode, where the application is talking directly to the DIMMs, or it can operate in memory mode, where it is transparent to the applications in the operating systems. So I typically like to start on the right-hand side in memory mode. So when the DCPM is running in memory mode, it is effectively acting as another layer of memory. So where we saw Werner talking about the pyramid earlier on, it's filling that gap between SSDs and memory, and it's operating transparently. So you still have your DDR in the system, but the Optane backs that DDR, and the DDR acts as a cache into the persistent memory. So in a two-socket system, for example, you can install up to 6 terabytes of this persistent memory, and then you can have workloads that use that full 6 terabytes. It also comes in 128, 256, and 512 gig modules. So that would give you a 1.5 terabyte, 3 terabyte, or 6 terabyte two-socket systems. And when it's operating in memory mode, where the persistent memory is handling all the caching for the DDR as well, there is very easy adoption. No code changes required, no operating system changes. It is just presenting to the operating system that you have potentially 6 terabytes of main memory in the system very affordably. You can also operate it in app direct mode, so in memory mode, it is volatile. So when you reboot the system, the data that was in those modules is no longer visible. So it's volatile. You can also operate it in app direct mode or storage mode on the left-hand side. And in this mode, it is persistent. So it survives the data on the module, survives reboot and power cycle transitions. So you can use it as storage here. You can make a file system on it. You can just treat it as a very fast block device or a very fast character device in the operating system. So what this allows you to do is to have very high speed storage. Because you can fit 12 of these into a two-socket system, it's effectively striping over 12 drives. So you're getting the performance of like 12 SSDs into your application. The other way that it's being used is to provide much higher availability. So if you look at something like SAP, it stores the column indexes on the persistent memory modules. And then when the SAP HANA system reboots, those in-memory database indexes are already available. The HANA database doesn't need to rebuild those. Or if you're doing in a high-performance compute use case, you could do something like a checkpoint restart. So where you're periodically checkpointing your application and your computations, and then if something happens to the operating system or the system, you can easily restore to that last checkpoint. And as I mentioned, it provides significantly faster storage. So the key thing here is you can either treat it as memory or you can treat it as storage. It does have the flexibility to do both modes simultaneously, but typically we see customers choosing either one mode or the other mode. Next slide, Werner. Now we've got a very significant ecosystem taking advantage of this. Obviously on the inside, we've got all the hardware vendors, so all the usual OEMs, and also the Intel channel products, which XENON represents. Then Intel also works very closely with the cloud service providers and the comm service providers. So we're starting to see persistent memory equipped instances showing up in things like Azure and Google Cloud, and some of the other cloud service providers. But also Intel works very closely with the software and the solutions layer to enable the ISVs and the applications to take advantage of the product. As we mentioned with SAP HANA, we've worked very closely with them for many years, getting ready for the product. It's supported by VMware and the Linux kernel. And also we're seeing things like Oracle with the Exadata 8M products, also including persistent memory in those solutions. Over on the very left-hand side, we've got things like Kubernetes, Cassandra and Apache Spark, we already mentioned. All of these products have been enabled to make use of this technology. Next slide. Now, the point of this slide is to show you that this isn't just a one-off. This is a very strategic technology for Intel. So on the first column, or the first product today, the code name of the product was Apache Pass, the Optane persistent memory technology, as it's now called. And we also have the data center P4800X NVMe drives built on that Optane technology. And then we have our traditional NAND products. So we've got products addressing all levels of that pyramid in our portfolio. The key logo there is second generation Intel Xeon Scalable. So this is the code name of Cascade Lake. So when you look at the CPU model number, it should have a 2 in the second character. The Skylake, the first generation scalable, does not support the Apache Pass product. Coming later in the year, early next year, will be Cooper Lake and Ice Lake. We have a next generation called Barlow Pass. This is a public slide. Google is your friend. So pretty much any of those code names you can see there, you can punch into Google and something will come up. Sapphire Rapids is the third generation, and we have already on the roadmap the fourth generation coming in some of those next products. So we do have a long roadmap with multiple generations of this technology coming to the servers. So with that, I'll hand back to Werner, and he can talk to you about some of the HPC use cases.
Let's look at some real-world applications here. We've picked here two because they're quite commonly used on high-performance compute platforms, quite typical engineering applications. One of them is LS-DYNA, which is quite widely used in the car manufacturing and design space for crash test simulations, for example. And OpenFOAM, of course, is a very popular computational fluid dynamics code that's used for aircraft design, for example. And I'll show you that in a minute. So LS-DYNA was benchmarked here using Intel Optane persistent memory technology on a 2-socket system. You can see the detailed specs on the bottom, probably just to highlight, it was using Intel Xeon Gold 6248M CPUs. And so you see the 2 here, as Peter referred to, these were Cascade Lake CPUs, which therefore support Intel Optane persistent memory. And the simplified result here really is kind of representing 2 different configurations. The leftmost one here, which presents the normalized result, was using a 2-socket system with those Intel 6248 MCPUs with 192 gigabytes of DRAM, of DDR4 modules, and 2 SSDs in a RAID 0 configuration with 1.2 terabytes capacity each. The comparison run here then in the middle was performed with the same amount of main memory, 192 gigabytes of DDR4, but it was using now Intel Optane persistent memory modules based on essentially now in storage mode, in storage over app direct mode, in again a RAID 0 configuration. So that was essentially using the DC persistent memory modules as storage devices. And then the third one here was using 1.5 terabytes of Intel Optane DC persistent memory with the DDR4 memory and just SSDs here on the side. But the main important aspect here is that the Optane modules were used in memory mode. And here, without going into the details of the simulation and the model itself, the striking difference is that when the Optane modules were run just in storage mode in RAID 0, essentially like fast SSDs, we get only a kind of quite moderate speed up here. However, when for this benchmark, then the Optane modules were switched into memory mode, we had now, instead of just 192 gigabytes of memory, we had 1.5 terabytes of effective memory available to the system. And so this LS-DYNA run here for that specific model got a speed up of about 75%, so 1.75 versus the original run without any persistent memory over that initial case. So without making any modifications to the code itself or the model, we get a significant speed up here, which reduces the time to result, which increases how quickly the engineers can get results from the models, and the kind of model generation, simulation, post-processing, and learning from that cycle is sped up dramatically, which leads to faster results and therefore the possibility of faster go-to-market with the results and with the products that are being worked on here with, in this case, LS-DYNA, for example. So that's kind of one engineering application. The second example we want to show is OpenFOAM. OpenFOAM is widely used computational fluid dynamics code that's been used for aircraft design for a really long time. And as you might appreciate, aircraft design takes a long time because it obviously has to be designed very carefully. It has to be designed very well. And it's really nowadays not just test-based, but it's really a simulation-based process. And when you kind of look at the time and effort that's required for such a project, there's a lot of simulation work that goes into the design of such new aircraft and aircraft components at the very beginning of the project. And the faster the engineers can obtain the results there, the more they can speed up the process and speed up the time to market for this new product. And the real challenge is that the design spaces are huge. There's a huge number of parameters in those models and in the designs which the engineers are evaluating. And so it requires hundreds and thousands of simulations, even with automated optimization processes, which will use different algorithms to optimize the design. It still takes a huge number of runs. And that just accumulates to quite a long time to go through these simulations. And so any way to speed up the process of these simulations can in the end save months or even years for such a long-term project. So for the specific example here, that's the simulation of a wing design from a NASA high-lift prediction workshop. So these are kind of standard examples that are quite commonly used in OpenFOAM. And it's here using a specific turbulence solver with a low Reynolds number, which is appropriate for such an aircraft design project. And the mesh itself is then partitioned into 224 subdomains, which are simulated on a cluster. So OpenFOAM then, now what we're looking here in the comparison really is a setup where on the one hand, we have a classic HPC architecture with a parallel file system based on Lustre. Each OpenFOAM process, which takes care of one of those 224 subdomains, writes its output to a parallel Lustre file system. The data is then organized in a directory tree with the results per time step, and that way it's then made available for post-processing from any node. And we want to compare this here for this example with a Intel Optane persistent memory setup, which writes the output now to these persistent memory modules in app direct mode. The data is organized again in one big directory tree, and the data is then available on each node for post-processing, or it can be collected to a global file system afterwards. But the real challenge kind of behind this way of how OpenFOAM goes through the simulations and saves the data is that it creates a pretty big load on the I/O system. And this is also something that we see quite often in deep learning and AI models today, which have huge data sets and create high load on the I/O systems. And the same is true for large database systems, and then the analytics which are run on top of them, as Peter has alluded to before. So what's now the result of these benchmarks? So there's a comparison here you can see on the bottom with 3 nodes, 5 nodes, and 10 nodes. And it shows here the time of execution for a very kind of short period of kind of simulated time, where we're writing the results after every 5 time steps. So what happens then on the 3-node system, the difference is not very big. You can see here a execution time of about not quite 10,000 seconds. On the 5-node system, of course, the simulation time goes down, and on a 10-node system, it's even faster than that. But what you can also see is, as we use more nodes in the cluster to solve this problem in parallel, the Lustre storage system does not scale very well. And we're actually losing time. The simulation time does not go down as quickly as we would want to, because the Lustre storage system there cannot keep up with the I/O coming from these models. Whereas the system with the Optane memory modules scales very nicely and linearly here down as we go from 3 to 5 to 10 nodes. And in the end, we end up with an advantage of 40% for Optane DC persistent memory modules, writing the results every 5 time steps compared to the conventional setup with the Lustre system. And that really means that the execution time is 40% lower, which means we can run then more simulations in a shorter time and be more efficient getting through all the modeling for this design project. The difference becomes even bigger when we look at writing out the time step, the result at every time step. That really depends on the type of post-processing that's required, if that's what's needed. And if that's a requirement to save the output data at every time step, we can see that in this case here, the Lustre parallel file system can't even keep up with all the I/O that's happening. And the simulation time actually goes up as we go from 3 to 5 to 10 nodes, because the I/O to the storage system just kind of overwhelms it and creates a bottleneck. Whereas in the case with the DC persistent memory modules, we can see a very nice, almost perfectly linear scaling here from 3 to 5 to 10 nodes. And now the simulation time goes down to here about 3,000 seconds compared to, let's call this 21,000 seconds. So there is a factor of 7x difference between the setup with the Lustre parallel file system compared to the configuration with the DC persistent memory modules. And so this really kind of shows the performance and the power of this new architecture with the DC persistent memory modules in such an HPC cluster for a workload like OpenFOAM here. So I hope that gave you some idea of what's possible when we use this new technology in new servers for HPC workloads and various other workloads which we've mentioned in this webinar today. And now would like to invite you to give this technology a try and run your models and your workloads on the POC equipment which we have available. So for proofs of concepts, for your experiments, for your tests, we'll have two systems available. One is a conventional large memory system with 1 terabyte of memory with the corresponding price tag attached to it, which has 16 64 gigabyte memory modules. That, of course, provides a lot of performance, but it has a pretty hefty price tag. But you'll be able to compare that to a 1 terabyte system with 8 Intel Optane 128 gigabyte memory modules. And overall, the system architecture is really the same. We're using the same platform. We're using the same second generation Cascade Lake CPUs. The main difference really here is in the memory configuration. And we'll also have some storage, of course, to hold your models and to store your data and appropriate network connections, and we'll give you remote access to these systems. But these two systems will allow you to really compare large memory systems as they're conventional designed with an Optane system that has that is a lot more cost effective for such large models and large workloads. Of course, we can also go back to a comparison and run it with much smaller memory equipped in the systems, so that you can also just see how much speed up you get from an existing server and adding Optane modules to that. So these are the two base configurations, and would like to invite you then to get in touch with us, to follow up with John and schedule your POC so that you can test your workloads and your codes on these systems. We'll also have Intel compiler licenses available so that if you use open source code or you have your own code, that you'll be able to do code optimization. You can use Intel vTune for profiling to measure the memory bandwidth, for example, to find hotspots in your code and to really optimize your code here on these platforms. So with that, I'd like to thank you here for your attention. I have here the contact details up so that you can contact us, and in particular John, to follow up concerning the POC. And with that, I'll hand it back to John to open for questions.
That's great, Werner. Thank you so much. Look, there's been a couple of questions into the chat, which I will toss over to you guys. The first is how do you switch between the modes, the MM and the AD? Is it possible to switch when the system's live, or how does that happen?
I guess that'd be a question for me as the Intel person. Yeah, so that is done using the configuration tools. It does involve a system reboot. So You just tell the system how much you want for memory mode, how much you want for app direct mode, whether it's 100% one way, 100% the other way. And then when you reboot the system, it will automatically configure. Obviously, any data that's stored on the persistent memory modules gets destroyed at that point as well. So be sure that you back up whatever data you did have on there if you're switching from app direct. But it does involve a reboot cycle to do that.
Yeah, that makes sense. Very good. A follow-up question to that, does the application need to be app direct enabled?
So I'll also take that one. So the application itself, as we said in memory mode, is completely transparent to the operating system and the application. As far as the application and the OS is concerned, it simply has that amount of memory that's presented from the Optane persistent memory. As well in app direct or storage over app direct mode, because you're just treating it as a block file system, you can use the traditional Linux or Windows tools to create logical volumes across the modules and just build a normal XFS or ext file system on those modules, in which case the application doesn't need to be modified at all either. It is purely just seen as a POSIX file system. There is another mode in App Direct where the application can talk directly to the module using the PMM API. So this is open source API. You can find it on the internet. And the modules you can actually talk to at byte level addressable. So if you did have an application where you wanted to write directly to and read directly from the modules in byte or cache line addressability, then you can also do that with the PMM API. That one does involve modifications to the application, obviously.
Yep. No, that makes sense. Great. Thanks, Peter. The last question here is probably for you, Werner, and leads on from that. What HPC applications are coded specifically then to take advantage of App Direct? Do you know of any that have already made that adjustment?
So there's a lot of applications which can take advantage of the memory in memory mode, which then, as Peter already suggested, do not require any modifications. And so there, the nice thing is that no code changes are required. The applications can just use much more memory now, and you can run much bigger models or much finer meshes or multiple models at the same time. So that's kind of the easiest way to take advantage of it. The second option there is, as was mentioned and shown in the benchmark, to use the storage over App Direct mode, where we can have now a very fast, essentially local file system on the Intel Optane persistent memory modules. And the reconfiguration for that is really quite easy, as Peter just described. And the final step then is to really use the PMM API to talk directly to the memory modules in the byte addressable way. There are more and more applications which are starting to implement that, but that's kind of really just in the process. And especially some of the open source projects, they're just starting to implement that. But it's really right now, one of the easiest ways is just to take advantage of the better economics of the persistent memory modules and essentially add them to expand the memory capacity of the servers without having to pay the prices for DRAM. But stay tuned, and more applications which will take advantage of that already, or which will then be optimized for app direct mode, will be coming, and we're happy to kind of follow up. And especially as we then have hopefully lots of people interested in the POCs, who then can investigate in detail which workloads are you running, which applications are you looking at, and we'll be happy to assist in checking then if there are new versions which support the different modes for the Intel Optane persistent memory module. So we'll be there, we'll lend a helping hand, and be happy to work with anyone who then wants to run their POCs.
Great. And we've got another question that's come in. How does the endurance compare to NAND?
Yeah. Peter, you want to comment on that?
So the endurance of the actual product, because it's based on the 3D crosspoint memory technology, is very high endurance. But yes, it's not the endurance of DDR. So the management tools give you the ability to understand, all right, well, how is the endurance going? But it has been designed specifically with a memory use case in mind. So the products are designed with very high number of cell writes built into the product. So yes, it's not as good as DDR4 in endurance, but it has been designed with a memory use case in mind.
Maybe just to follow up on that, I think the second important kind of comparison there is, of course, with conventional flash memory and or flash SSDs, which in principle you could say, well, I can also use a flash drive, flash SSD with some software tools as memory. But that's where it becomes really challenging for TLC, and especially for QLC flash SSDs, which have an very, very, let's say, challenging endurance. And therefore, they are really not suitable for such kind of memory expansion applications. And Intel Optane is really the only option there to give you a much larger capacity and really kind of give you these large memory systems in even just 2-socket servers with up to 6 terabytes of Optane persistent memory modules at a price point that's a lot more affordable than DRAM. And just to give kind of a general guide to that, we're looking at about in the order of 2x difference between DRAM and Intel Optane persistent memory. It then depends on the specific configuration and the drives which are used, and but that's kind of as a rule of thumb, that's what you're looking at. And so that's why Intel Optane is really the big enabler in that space.
Beautiful.
Yeah, so I don't have the exact endurance number on the top of my head, but feel free to reach out to me and I can dig it out of the product data sheet.
Okay, great. So I think that's all the questions. So I think the takeaway from this tech talk would be that you've got the opportunity to run your systems maybe 40% faster at half the cost. Would you guys agree with that?
Yeah, I'm sure there's, as we've shown, there's workloads where that difference is maybe even bigger, or we can make it even more cost effective. But yeah, that's probably a fair rule of thumb.
Yeah, and so typically where I'm seeing it used is some customers have applications that require that large memory footprint that just it wasn't economically feasible to even run an application like that. So it didn't justify the expenditure of buying an 8-socket box to get a 6 terabyte memory footprint. So now using Optane persistent memory, those kinds of applications can be run quite economically. So it's really bringing a new class of application into the market as well.
Fantastic. Well, that's brilliant. Well, and as so we've got these systems ready to go for POC, so we hope to hear from you guys soon. I want to thank Peter and Werner, for your time, and for everyone who attended, taking time out to listen to this fascinating tech talk. Thanks so much, and that's all from now.
Thanks
Thanks
everyone.
all.
Bye for now.